The renewable energy sector is growing rapidly, with Britain marking the first 2 months since pre-industrial revolution it has gone without burning coal just this week. In order for countries to reduce their carbon impact, more of the global energy demand will need to be satisfied by wind power. Because of its paramount importance, we were tasked with designing a horizontal axis wind turbine with the following constraints: a maximum tip-to-tip diameter of 450 millimeters and a maximum angular velocity of 3000 rpm, a maximum tip speed ratio between 3 to 8. The wind turbine must also be printed as a single part in a box of size 400 by 150 by 100 millimeters.
We started off by choosing the number of blades. Aerodynamically, a one-bladed turbine is the most efficient. However, this requires a counterweight for balance and to address stability issues. Any number of blades greater than 3 would generate the necessary wind resistance that will consequently make the turbine less efficient due to interference between the blades. 3-bladed turbines are considered to be the best compromise between energy yield, stability, and durability for real-life wind turbines. However, for smaller non-commercial applications where wind velocity is rather small, 2-bladed turbines prove to be more suitable. Studies for small-scale models show that a 2-bladed turbine yields more energy than a 3-bladed one, as there is less interference from the blades. Moreover, a 2-bladed configuration will also make the turbine fit better within the dimensional constraints. Hence, a 2-bladed design was chosen for our application. The number of blades also dictates the optimal tip-speed ratio, or TSR. Research shows that for a 2-bladed turbine, the maximum coefficient of power, or CP, is achieved at a TSR of approximately 2 pi. The next step was to choose an appropriate airfoil cross-section for the blade. The maximum CP, as given by the actuator disk theory, is approximately 0.59, which is the best limit. In order to maximize CP for a given TSR limit, the lift-to-drag ratio should also be maximized along the blade. We therefore chose to analyze the SG series, particularly the 6040, 6042, and 6043 airfoils, which are widely used for wind turbines applications. CL over CD versus alpha graphs were plotted. The greatest aerodynamic performance for a Reynolds number of approximately 100,000 is given by SG6043 and SG6042. A two-bladed design has a disadvantage of gyroscopic precession, a phenomenon resulting in wobbling and unwanted twisting effects, placing extra stress on the turbine components. While SG6042 and SG6043 show comparable aerodynamic performance, research shows that SG6042 is regarded as being more structurally sound. Therefore, we chose this airfoil as it offered the best compromise between aerodynamic performance and structural integrity.
For maximum efficiency, circulation must be approximately constant along the blade. In a wind turbine, lift acts as a rotary motion which creates a power output. In order to achieve constant lift, the incidence of the blade must be constant. As the speed seen by the blade increases with distance from the rotational axis, the relative angle of the incoming flow varies along the length of the blade. Therefore, we applied a twist to keep the blade at the most effective angle of incidence and thereby maximizing the lift-to-drag ratio. Optimal twist angle and chord length were calculated using the Schmidt's distribution. We decided to optimize our wind turbine for a maximum wind speed of 12 meters per second. In order to not exceed the rotational velocity of 3000 rpm, a TSR of 5.76 was found to be a decent compromise between the aerodynamic performance and the project constraints. The design of the blade was further optimized using Q-blade.
We decided to add winglets to our design to improve its aerodynamic performance. The addition of winglets decreases induced drag at the tip by changing the downwash distribution. A Danish paper investigated the size of several different winglets using CFD methodology. They kept the cant angle constant at 90 degrees and set the sweep angle to 0. Having consulted several other research papers, we found that the optimal winglet design for our wind turbine is at an angle between 45 and 90 degrees and has a height that is 1% of the blade length.
The blades and nose cone of our turbine were created as one piece via a rapid prototyping machine that placed down hot fuse wires of ABS plastic. Because the plastic is fibrous, it's got a higher strength in the direction of the fibre in comparison to the transverse direction, which has an approximately 0.2 reduction factor in strength. This means that the optimum strength of the blade centrifugally would be when the fibres are actually aligned parallel to the blade, which was something that we couldn't achieve given the size constraints and printing direction of the box that we were manufacturing it in. However, our calculations show that the current design is strong enough to withstand the centrifugal forces and associated stresses of operation. We also took into consideration the bending moments and shear forces to be experienced whilst in operation. The analysis showed that they would be maximum near the root of the blade and 0 at the tips, which prompted our design of a high to low chord length from the root outwards. We also utilised the virtual work method to estimate deflections. Note that the turbine blades were modelled as simple cantilever beams, which provided a suitable approximation for this purpose.
We began by considering the design specifications which would guarantee the performance of the nose cone. Based on this brief, some initial ideas were developed. The first of these concepts featured a spherical design, with a dimpled surface, employed in order to induce a turbulent boundary layer, thus lowering the body's drag coefficient. An alternative idea followed the principles of the Hark series, a mathematically derived set of coordinates which, when used as a cross-section, allows a nose cone to achieve the lowest possible drag for a given length and volume. By evaluating these initial designs against the prescribed specification points, we decided on the Hark series nose cone. This was primarily due to the fact that, following consultation with a department technician, we found that the 3D printer's resolution would be inadequate to reproduce the 2mm deep dimples, therefore making their intended effect insignificant. Instead, the use of Hark coordinates compensated for this by reducing the nose cone's drag in its own right. We decided to incorporate a hinge mechanism within the nose cone. Following the project's volume constraints, our blade swept area rose by 7,859.64mm squared, reaping significant energy transfer rewards. Based on the project's constraints, a list of specifications were drawn up for the hinge mechanism. With these targets in mind, a series of initial ideas were developed. Concept 1 rotates around a plane inclined to the base of the nose cone. It's a unique solution which provides volume benefits whilst minimizing additional mass. Idea 2 uses a hinge mechanism, with its axis centered at the corner of the nose cone half. Latches are used, featuring arms that deflect and settle into grooves within the opposing nose cone half. This mechanism is fully incorporated within the sectional envelope, and therefore has minimal interaction with the oncoming airflow. We took the second concept forward, due to its comparative advantage against initial idea 1, which was deemed to be unnecessarily complicated and difficult to lock in place whilst resisting centrifugal forces. In order to perfect the tolerances for both mechanisms, small-scale prototyping was conducted. Through this, a 0.25mm tolerance between hinge surfaces was selected, and the latch design was iterated to include another arm, which limited displacement in a vertical plane, leading us to our final design.
It's worth mentioning that, to reduce possible extra drag, and for a better fit within the nose cone, we decided to decrease the chord length at the root of the blade. This, as well as the addition of winglets, may have slightly changed the optimal TSR, but this could not be fully simulated in Q-Blade. Finally, we also used Q-Blade simulations to check that the turbine was spinning clockwise.
The first step was to produce our hub. Our turbine design incorporated a hinge in order to maximize the radius whilst being within design limits. We glued the halves together to ensure the piece did not unfold. Any excess glue displaced outside the join was then sanded off. We then sanded the part down to even out the surface, especially the trailing edge, which came out very rough due to the limited definition of the rapid prototyping machine. A combination of wet and dry sanding was used with successively higher grids. Dry sanding to even the surface and wet sanding to remove any scratches left by the dry sanding. This is important to ensure smooth airflow. The hole for the hub had to be filed down slightly as the fit was initially too tight. Burrs were also removed from the QA and the hole for the hub to ensure tight fit. During manufacture, care was taken when sanding the nose cone to ensure that grooves in the surface were developed perpendicular to oncoming airflow. This triggers pockets of turbulence, delaying flow separation from the nose cone surface. The final stage of the manufacturing process was to coat the entire part in a thin layer of acetone. As a petroleum-based plastic, ABS is highly soluble in organic solvents such as acetone. The outer layer slowly dissolves and solidifies when the acetone evaporates, leaving behind a more uniform, stronger piece with fewer voids or scratches near the surface.
Unfortunately, due to the outbreak of COVID-19, we were unable to test our wind turbine. However, following Q-Blade simulations, it was estimated that a maximum coefficient of pressure of 0.43 would be achieved at a TSR of 5.76 at a velocity of 12 meters per second. Due to software limitations, we were unable to fully simulate the effect of winglets using Q-Blade. However, research showed that CP was increased with the addition of winglets, hence the final CP may have been up to 1.4% higher. Not letting the pandemic slow our engineering spirit, we put some thought into some future iterations. We'd be keen to investigate the possibility of removing the nose cone altogether from the design by blending the opposing blades into a single smooth joint. This could further reduce drag and moment of inertia costs. We could optimize the design by removing hinges altogether to reduce the number of possible failure modes. This could be replaced by a screw mechanism binding the two halves of the turbine together. Here, friction alone could replace the need for costly adhesive. In light of the COVID-19 pandemic, a useful application of our wind turbine would be addressing power shortages across the globe. Our turbine could be modified to generate power for a CPAP ventilator. Preliminary calculations confirm that our power output is sufficient to run a 140-watt Mackay Servo I ventilator. Of course, further research and testing will be required before the implementation of this concept, but it's an interesting premise with real-world applications. In the near future, with several governments pledging a large fiscal stimulus package with a renewable and sustainable focus, for example the €750 billion EU Green Recovery Plan, we hope that what we have learnt through the project should become particularly useful.